In this video, I go over the class question slides for Lecture 7, corresponding to Chapter 7 of your textbook. So the first one, go ahead and take a read of that question, pause it, and now I'd like to go over the answer. What's the shape of an equipotential surface for a uniform electric field? An equipotential surface represents the locus of all points at one and the same value of electric potential. So if you move a particle from one point on that surface to another point on the surface, no work is done on the charged particle. If you move a charged particle from one point on that surface to another point on that surface, no work is going to be done on that charged particle. I'll call it the test particle because I'm using it to test the electric potential. Because the work done is the negative of the change in potential energy. The potential energy is the charge of my test particle times the value of the electric potential. So if I'm moving from one point on an equipotential surface to another point on that same equipotential surface, then the two values of electric potential have to be the same. That is, at those 2 points, there's only one and the same value of electric potential. And so a good way to imagine testing this thing out is to move a charged particle around in the electric field and imagine how I could move it such that no work is done. In other words, what's the locus of all points I could move it to from one particular point such that no work would be done on the charged particle. Now, if I got a uniform electric field, let's see, get a pen up here. And I want to move a charged particle around on it such that the electric, around in that region where the electric field exists, such that the electric field does no work on the charged particle. Then what I have to do is move the charged particle along a path that is everywhere perpendicular to the electric field. In this two-dimensional diagram, that looks like a line, but of course I could just move the charged particle toward or away from us, and I'm still moving the charged particle along a path that's perpendicular to the electric field. So the collection of all the points to which I can move the particle to, say from right here, without the electric field doing any work on it, would be a flat sheet. So I could move the charged particle around anywhere on that flat sheet that I wanted, from any point on the flat sheet to any other point on the flat sheet, without the electric field doing any work on it, because every step of the path would be along a direction that's perpendicular to the electric field. So box wouldn't work. I can represent that by a square here, but if I moved it from here to here, for instance, some work would be done by the electric field, and hence I would have to get a value of work if I calculate it as the negative of the change in the electric potential energy, which, by the way, would be the charge of the test charge times the negative of the change of the electric potential. That is, if I move it from A to B, the electric potential at the negative of phi sub B minus phi sub A. Okay, so a flat sheet without doubt. Perfectly conducting wires. Okay, remember, everywhere in and on a perfectly conducting material, any object, doesn't have to be in the shape of a wire, but anywhere in and on the a perfect conductor, the electric potential has one and the same value. A and B are on one and the same perfect conductor. This is all one perfect conductor. All the points are connected to each other, so there's only one potential. So the difference between the two electric potentials is 0. How does the electric potential at B compare with the electric potential at A? The same as, so it's got to be this one. Not enough information, none of the above. Yeah, it's B. So we're going to do it this way. Alright, let's take a look at it. Depicted are two sets of connected perfectly conducting wires under static conditions. Okay, two sets of connected. So in other words, here all these pieces of wire are connected to each other. It looks like there's a piece here and a piece here that are connected to each other. And then separately, we've got a piece here and a piece here that are connected to each other. But this whole bottom configuration set of wires is not connected to this entire top set of wires. So the potential at B is 6 volts greater than the potential at A. VB, or phi sub B is minus phi sub A is 6 volts. Phi sub B is 6 volts greater than phi sub A. A particle of charge 1e. That's a positive amount of charge. The E is a unit of charge. An electron has a charge minus 1e. A proton has a charge of 1e. So this particle of charge 1e could very well be a proton. Is caused to move from point C to point D. We don't know how somebody did it. Maybe they had it on the end of a glass rod and they moved it from here to here. But somehow they did it. And point C is on a conductor and point D is on a different conductor. What is the change in the electric potential energy of the particle? Okay, now clearly they moved it from a point where the electric potential is 6 volts greater than the electric potential is at the destination, and hence the change in electric potential is between the 2 points is minus 6 volts. The change in electric potential energy is therefore minus 6 times the charge times volts. That's minus 6 eV. I'm going to go with A, minus 6 eV. So the potential energy is just the charge of the particle times the electric potential. We can make up numbers. 6 volts greater, I could call D 0 and C 6 volts. So it went from electric potential energy of 1E times 6 volts, that's 6 eV, to 1E times 0 volts, that's 0. From 6 eV to 0 eV, that's a change of minus 6 eV. If you don't like those numbers, you could do 106 volts here and 100 volts here. So it went from 106 eV to 100 eV. Once again, that's a change of minus 6 eV. Now this question about is that actually a unit of energy? The volt is a joule per coulomb. Energy, a unit of energy divided by a unit of charge, and this is a unit of charge. So yeah, the EV is equivalent to an E times J over C, and that is a unit of energy. If I wanted to get it in SI units of energy, I would write the E. The easiest way in my mind is to replace the E with what it is, which in SI units, which is 1.6 times 10 to the minus 19th coulombs. And if I did that, I would see that the coulombs would cancel out and I'd be left with joules, so it's clearly a unit of energy. It's a non-SI unit of energy, but it's a unit of energy nonetheless. So D is ruled out there. C, no way. And B, no way. In other words, this would mean both C and D are at the same value of electric potential, and this one says the destination point D is at a higher value of potential than the C. Note, well, I guess one of the things I skipped over here is when they say that B is 6 volts greater than A, that is the electric potential at B is 6 volts greater than the electric potential at A, that's the same thing as saying the electric potential at C is 6 volts greater than the electric potential at D, because this is all one conductor. Whatever value of electric potential we have at B, that's the same value that we have at C. Same thing for this. This is all one conductor right here. All these wires are connected to each other. So whatever potential we have at A, we have at D. Remember, at all points within an ideal perfect conductor under static condition, the electric potential has one and the same value. So once again, if this is at 0 volts, and this is at 6 volts, then everything here, including C, is at 6 volts, and everything here, A is at 0 volts, everything here is at 0 volts, including D. if B is at 106 volts and A is at 100 volts, the fact that B is at 106 volts means that everything here, including C, is at 106 volts. And A being at 100 volts means that everything here, including D, is at 100 volts. So saying that the electric potential at B is 6 volts greater than the electric potential at A is identical to saying the electric potential at C is 6 volts greater than the electric potential at D. Alright, last one. Imagine a ping pong ball and a rubber ball. Let's go the ping pong ball and the rubber ball. Both of them have been coated with conducting paint. Treat them as ideal conductors. I use a high voltage power supply to cause each in relative isolation to have a potential of 2400 volts. Okay, so let's take a test charge, move it out to infinity where it has 0 potential energy, and I move it in right up to the surface here, and let's assume they both have the same amount of charge, but I move to the surface here, and this one really is at 2400 volts. So assume for the moment they both have the same amount of charge and that the baseball is at 2400 volts. Now, that means that the amount of work that I had to do was 2400 volts times Q to bring that in there to make it so that the charged particle that I moved in there, the charged particle of charge Q, had Q times 2400 volts. Now the thing is, in order to, in the case of the ping pong ball, by moving it just as far right there, if it had the same amount of charge, then I would already be at 2400 volts. But then I would have to keep on moving it here, and so I'd have to do more work to get it that close to the charge. Another way of looking at it, so in some sense I'm getting it closer to the amount of charge. I would have to do more work, so the charged particle would be at a higher potential energy, and that would mean the electric potential here would be higher, and therefore since that contradicts the given. If I assume that they both have the same charge, then the ping pong ball has a higher electric potential, higher than 2400 volts for instance, so the ping pong ball must have less charge. At that potential, which has more charge, the rubber ball must have more charge. Another way of looking at this is the electric potential outside right up to the surface is the same as it would be if instead of a baseball coated with the charge spread out over, all the charge were concentrated at the center. So that's KQ over R. And therefore, at a distance equal to the radius of the baseball, I would have a certain value of KQ over R sub B. In fact, it would be 2400 volts, pretending that all the charge is concentrated at the center. If they do the same thing here, once again, pretend or assume for the moment that it's the same amount of charge, then I would have out here the electric potential would be 2400 volts, but to get to the surface of it, I have to move closer and closer to that imaginary fixed amount of charge, and hence the electric potential would be greater right here. But the electric potential has to be the same, and therefore the charge has to be less. So once again, we say the rubber ball has more charge. I guess you could look at it right here. If when I get to the surface, I'm closer to that to the center there, where I can say outside, including at the surface, the electric potential is the same as it would be if instead of the actual charge distribution, uniform distribution of charge on the baseball, all the charge were concentrated at the center. For the baseball, I would be out further from the center, and so RB would be bigger, and therefore Q has to be bigger if KQ over R is the same for both of them. So the rubber ball has to have more charge. Alright, that's a couple of different ways to look at the same thing, but in any case we find that the rubber ball has more charge. Alright, that's a wrap for this class question slides. The class question slides video associated with Chapter 7.